Welcome everyone on Gamma seminar. Today we have a pleasure to host Professor Agustin Moreno from Heidelberg University, and he will give a talk, a symplectic viewpoint on the restricted three-body problem. Professor, the floor is yours.
All right, thank you for the invitation. It's a great pleasure for me to give a talk in the seminar. Hopefully, I'll get to meet you in person at some point. So today I will discuss, as the title suggests, a modern viewpoint on a very old problem that most of you probably already know. So I'm talking about the three-body problem, of course. Everything that I'll say today will be contained in a book that I recently wrote and hopefully will be published at some point by Springer. So it also touches on the same theme, sort of using modern tools from symplectic geometry to try to address this very old dynamical system. And what I will say today is based on joint work with two people. So one of them is Otto, who's my close collaborator in Seoul, and my student Arthur Limoges, who is just graduating next month in Heidelberg. Okay. So I know that this is kind of a mixed crowd, so I tried to make the talk as self-contained as possible. If I say something that you're not familiar with, then please interrupt me, and I'll be happy to say more things. Okay. So let me start then with the setup. So what's the problem that motivates all the math is the restricted three-body problem. So in the setup, we have three objects, which I will call the Earth, the Moon, and a satellite, but of course you can call them whatever you want. They have certain associated masses, and the idea is just to leave them to interact with each other according to, Newton's second law, so gravitational interaction. So as we all know, this is a very complicated dynamical system, very different from the two-body problem, which is an integrable system we can just understand very well. So some classical assumptions that people have made in order to try to attack the problem or to simplify it are the following. So the first one is we consider the restricted case. So that means that the mass of the satellite is zero. So in other words, it's negligible when we compare it to the other two, which we call the primaries. Um, so this sort of simplifies the equations, of course. Then the second assumption that we make, which is an approximation of the real scenario, is the circular assumption. We assume that the primaries, the Earth and the Moon, they move in circles around their center of mass. So in general, they would move in ellipses. This is, again, the two-body problem or the Kepler problem. And then the third case that people have looked at a lot historically is the planar case. So when the satellite moves in the ecliptic plane containing the Earth and the Moon. So this is a lower dimensional problem than the spatial case. The spatial case is where the satellite moves in R3, so in a three-dimensional space. So that will be the problem that I will be mostly interested in, the high-dimensional problem, okay, the spatial problem. So the goal is to study the motion of the satellite. I mean, in a broadly understood sense, of course, we will have to ask specific questions as we go along. What does it mean to solve the three-body problem? I mean, that's a very difficult question to answer because we know we cannot integrate the equations. So one of the particular things that I'll be interested in is periodic orbits. Okay, so because as Poincaré has pointed out, these are the most basic dynamical objects that we can be interested in. Okay. All right, so this is, of course, a Hamiltonian system because of the assumption that we made on the circular motion of the primaries. We can actually go to a rotating frame in which they are fixed. The positions are fixed. So E, for example, is in the x-axis, where the x parameter is called mu. The x sort of coordinate of E is called mu, and then the Moon is in the same x-axis but opposite. So the origin is the center of mass, and the Moon is at -1 plus mu. Now the positions are fixed. But what happens is now the gain is that the Hamiltonian in this new frame becomes autonomous. It becomes time independent. So that's a conserved quantity, therefore. So it has this expression. So there's a kinetic term, of course, representing free motion. There's a gravitational potential for each of the primaries. And then usually you would stop there with the Hamiltonian depending on time. But now the price that we paid is because of this rotating frame is the appearance of this angular momentum term here, keeping track of the rotating rotating motion. Okay, so now, but the gain is that it doesn't depend on time. Here, usually we normalize, so we assume that the sum of the mass of the Earth and the Moon is 1. So this mu parameter, which is normally the mass ratio, you can just think of it as the mass of the Moon. Okay. The planar problem, so here Q and P are position and momentum, as always in classical mechanics. So Q has 3 coordinates and it's the same thing as P. So the phase space is 6-dimensional in this case. If we draw the last 2 coordinates, so P3 and Q3, we set them to 0, then we get the planar problem, which is, of course, a flow invariant subset when you write down Hamilton equations. You can see that by the physics or just from the form of the Hamiltonian itself, noting that the angular momentum turn doesn't depend on these coordinates. So the 2 parameters in the problem, mu, so the mass of the Moon, and then the Jacobi constant, which I will think of as a value of the energy. I mean, there are different conventions for different people. Engineers call the Jacobi constant something else. Maybe there's a -2 somewhere. I will just simplify things and think of the Jacobi constant as the energy of the system. Okay, so if you do the computations, and this was done a long time ago, maybe 200 years ago, by Euler and Lagrange, you will find that there are precisely 5 critical points of the Hamiltonian, which are classically called the Lagrangians, and they're ordered according to increasing value of energy, L1 up to L5. So here, what I'm showing in this picture is the energy values for the different critical points. So the horizontal axis is the mu axis and the vertical axis is the energy, so the Jacobi constant. And here, h of L1 is the lowest energy value, the first critical value of the energy. And then you see L2 and L3, which they swap roles, of course, because as you cross mu equals 1/2, there's some symmetry in this picture with respect to mu equals 1/2, of course. And then L4 and L5 all both have the same energy. So I will call everything that's below L1 the low energy range. Okay? That will be the range of energies in which I will do some math. Okay, I will not be doing anything for other energy ranges. Mu equals 0 is the rotating Kepler problem. So this is the two-body problem, but where you are still in a rotating frame. This is an integrable system. It's very easy to understand mathematically. So that's one of the limit cases in the setup, which one uses as a starting point usually in most approaches to this problem. There's also a fact that as you go to minus infinity in the energy, as you go down in energy, you need to there's a regularization process that you need to do, but after that you see that as a limit you recover the honest non-rotating Kepler problem. So the two-body problem is also a limit case of the setup. Okay, so those are the two integrable systems that appear naturally when you study the general problem. Okay, and then this is a bit of a topological picture. I will be interested, as I said, in the low energy range, so with the energies below L1. What happens is if we look at the classically allowed regions of motion, so the so-called hill regions, so these are just you look at the energy level sets and you project down to configuration spaces, to the positions, to the space of positions. You see that when you're below L1, there's precisely 3 connected components to the hill region. So what this says is that if you start, say, near the Earth and you don't have enough energy, then you will stay forever near the Earth. So those correspond to satellites we actually put in orbit near the Earth, like Elon Musk's, say. And then there's a similar picture for near the Moon. If you start near the Moon, you don't have enough energy, you stay there. So if you want to place, I don't know, people in orbit, this is kind of trajectory they will have to consider. And then if you the same in the same energy range, but you start sufficiently far away, then you don't never get close enough to the Earth nor the Moon. So you're an asteroid, and you're one of the good asteroids in the sense that we don't are not worried that you will hit the Earth. So we don't have to keep track of you all that much. Okay. And you see, because of the singularity and the Hamiltonian, because of the fact that the gravitational potentials are singular at collision, so when the satellite crashes with one of the primaries, the energy level sets are non-compact. This is because conservation of energy. So as you get closer and closer to the Earth, the potential is sort of exploding, but therefore the kinetic term needs to also explode to keep up. And you see this sort of explosion in the vertical direction, sort of in the direction of momentum. Okay, this is something that for dynamics, it's not so great to have a non-compact manifold in which you're doing dynamics. So we will actually have to deal with that, and basically we'll have to regularize collisions. So this is what I'll explain now. Um, but before that, this is just to give you an actual sort of picture of what the level sets of the potential look like. So here in the center, you see the bigger primary, let's say that's the Earth, and then here you see the smaller primary, the Moon. And you see that the L1, L2, and L3 are all situated in the x-axis. They're the collinear points found by Euler. And then you see L4 and L5, which are outside of the x-axis, and they actually form the vertices of an equilateral triangle when you put in the two other primers. Okay, and they're symmetric with respect to each other. And you see, as you cross L1, you see the appearance of this sort of connected sum hill region. So before there were two disks which were disjoint from each other, but as you cross, as we know from Morse theory, there's a handle attachment that occurs. So you see this sort of new level set, which now allows you to cross from the Earth to the Moon, say. So if you input enough energy, then you can sort of send the satellite from here to the Moon. Okay, so that's basically the setup. As I said, there's some issues with the collisions. I mean, the Hamiltonian is singular, a collision where Q equals E or Q equals M. Therefore, the momenta has to explode because of conservation of energy. And, from an engineering point of view, collisions are, of course, terrible. Imagine that you've been working on a satellite that's worth millions and millions of dollars, and then you crash it against the moon, then somebody will definitely yell at you for that. But for us, from a mathematical point of view, we don't really care too much. So we'll do a very sort of naive thing. When the satellite will come and crash against the Earth, say, then we'll just add a trampoline. We'll just like make it bounce and go back from where it came from. So that's basically what regularization is all about. Of course, you need to change time. You need to slow time in order for you to sort of continue the dynamics after the collision. So this is roughly what regularization does. And more formally, and this is a regularization scheme by Moser, who observed that the regularization that that will explain now, the regularization of the Kepler problem gives you a geodesic flow on a two-sphere, so everything is periodic. But for the more general case, the dynamics will be more complicated, of course. So formally, this works as follows. So you take your QP coordinates, you switch them. So you put a minus sign in front of the P and switch the order just to preserve the symplectic form. And then you take the inverse of the stereographic projection. So you add a point at infinity, and then you get new coordinates on T star S3, so on the cotangent bundle of.
Sorry, so Moser regularization is only about two body collisions?
Yeah, yeah.
Okay.
So
and there are generalizations of this regularization to more bodies, more collision. Yeah.
So that's a good question. So first of all, the first observation is that in this problem we don't have collisions of three or more bodies because we just fix the dynamics of the Earth and the Moon to move in circles. We only care the dynamics of the satellite, so we can only have binary collisions. And yes, there are other ways to regularize triple collisions. Say, I'm not very familiar with those, so I don't want to say too much. But I know there's whole sort of literatures on regularization schemes. This is a very rich area.
Okay.
Quite
Thank you.
interesting. Yes. Okay. So then you do this, right? So the point here, intuitively, I'm just adding a point at infinity where p equals infinity. So that's a collision locus. So the geometry is a bit like this. Um, so first of all, okay, you have to do these transformations, but then you also need to regularize the Hamiltonian. So there's a way to do that. I'm not going to write down the formulas, but there's a Hamiltonian Q on T star is 3 with the property that the zero level set of that Hamiltonian Q is a compactification of the original level set for your original system. So you have to fix the energy C, and then there's a corresponding Q for that C. And topologically, what happens is that the topology of a level set now becomes S3 times S2. So it's a five-dimensional level set, as we know. We started with a six-dimensional phase space. We fixed the energy, therefore we have a five-dimensional energy level set. But now what I'm saying is that near the Earth or near the Moon, when we regularize, the topology will be S3 times S2. So really, it's just the way to understand this, or one way to understand this, is the following. So what I'm drawing here is a three-dimensional sphere where P is now varying, because remember we switched P and Q, so now you should think that P moves on the base as opposed to moving in the fiber. So now P moves in this three-dimensional sphere. When you go to infinity, that's exactly the point that we added. That's the collision locus. And then the fiber of that point is the positions of the allowed positions. So infinitesimally, what's happening is that I'm adding all the possible directions in which I can collide against the Earth. So that gives me a two sphere of directions. If I fix the energy, right? If I don't fix the energy, then it's just a plane, it's just a fiber over that point. And then you see here also this vertical S2, so this is a two-dimensional sphere that also goes through collision at infinity. That's my picture for the planar problem. So that's the invariant subset corresponding to the planar problem. The plane also has collisions, therefore it has to go through the collision locus at infinity. Okay, so all that's happening is I'm adding this sort of fiber at infinity, which is a Lagrangian, so the symplectic form vanishes on that fiber, and then that implies that this two-dimensional sphere of infinitesimal directions is a Lagrangian in contact geometrical terms. So that means that it's sort of it's tangent to the contact structure in the Unicode tangent bundle. I mean, I'll say a bit more about that later. But sort of this is roughly the geometry and the topology of the situation. Okay, so now I have a compact manifold, I have some dynamical system, this five-dimensional manifold, which I'm trying to say something about. Okay. All right. So let me just, I probably don't need to say much about this, but I think I will anyway. So let me just remind you that a contact manifold is an odd-dimensional manifold which comes with a hyperplane distribution, which is called a contact structure, and it's written globally. I want to think of it as written globally as a kernel of a one form alpha, and this alpha is a contact one form. This should be a one and not a anyways, so alpha is a contact one form, satisfies the contact condition. So alpha wedge d alpha to the n is a volume form which is positive with respect to some fixed orientation. Okay, so this of course appears in mechanics, and whenever we have a contact form, we consider the so-called vector field associated to it, which is determined by two equations. So first, it has to be in the kernel of the alpha. The kernel of the alpha, because of the contact condition, is one-dimensional. So it's a one-dimensional line distribution in the manifold. And so I'm just picking up a direction in that line field. And now the second condition is a normalization condition. So I just want that direction to be normalized by alpha. Okay, so this gives given alpha, we have a unique dynamical system given by the rate field on the manifold. Okay, and the example to keep in mind, which will appear, is you take a Riemannian manifold, look at the unit cotangent bundle, so of those covectors with norm one. This carries a standard contact structure. So you just take the Liouville form in the cotangent bundle, restricted to the unit cotangent bundle. That's a contact form for a contact structure. Okay. So now, if, for example, a rave dynamics for that contact form is a geodesic flow, but then you could also have many other different dynamics, rave dynamics for the same contact structure. So you vary the contact form, but you fix the contact structure. Okay? Given a contact structure, there's many contact forms for that. Just take any alpha and then multiply that one by a positive function. So that gives you very different dynamical systems in general. Okay, so that will be sort of the key point for what comes now, because what comes now is I'll say, well, we'll be able to view the dynamics in the lower energy range and near the primaries for the CR3BP as a rate flow for some contact form for the standard contact structure. So that's sort of the content of the next theorem. So this is a result by Peter Albers, Urs Frauenfelder, Otto van Kurt, and Paternine. So this is from 2012. So these people did it for the planar case. And then Cho, Jung, and Kim did the same thing for the spatial case some years later. And the content of the theorem is, as I said, well, now there's basically a contact structure on the level sets, and then the dynamics, the original dynamics for the CR3P is given by a rate flow. So a bit more formally, so you take the regularized bounded energy components for subcritical energy. So these are just, remember, the components of the energy level sets which project to these neighborhoods of the Earth and the Moon. And then you consider the same thing, but for the planar problem. And what this theorem says is that this compactified level sets carry contact structures. So they're isomorphic as contact manifolds to the unipotential bundle of S3 in the spatial case with the standard contact structure on this unipotential bundle. This is, of course, for subcritical C. And the same thing for the planar case where now you replace S3 by S2. Okay, so this is a 3 manifold inside a 5 manifold. In all the above cases, the planar problem is, of course, it's a subproblem from a dynamical point of view, but it's also a subproblem from a geometric point of view. So it's a codimension 2 contact submanifold. It just means that the contact structure on the submanifold is a restriction of the contact structure from the ambient manifold to the submanifold. And now the real point of this content the real content of this theorem is that the flow of the original system is given by the flow of a ripple for some contact form. Okay, for some contact form for the standard contact structure. So in
Yeah,
other words,
sorry, may I have a question?
yeah,
Does it follow from the fact that I mean the proof is that like you introduce the Liouville vector field and it's transversal to the level set of the Hamiltonian, which in this case it is transversal, so the
yeah,
level set is a okay.
yeah,
Okay,
that's
thank
exactly
you.
the proof. Yeah, it's a computation. I
Okay,
mean, conceptually,
yeah.
it's a very simple thing. Yeah, as you said, you take you regularize. Now we have a cotangent bundle. There's a natural Liouville vector field, and you just check that it's transverse to the level set. It's just a complicated computation, but yeah.
Okay, thank you.
So yeah, so this is that's a proof conceptually. As I said, it's telling us that this flow that we started with is actually a rib flow for some contact form. You don't really have much control over the contact form. You know that the kernel is the standard contact structure, but in general, it could be quite complicated. And it changes. I mean, the contact form depends on the parameters. It depends on mu and it depends on C. So now the idea is now we can try to use contact and symplectic geometry in this old problem. So this is sort of opening up the gate for that. So, we have tools for that. We have holomorphic curves, we have Floer theories, we have a bunch of different tools. And now the big general direction is to try to use those tools to try to say something about this problem. So the sort of the philosophy of what we're trying to do. Okay, so before trying to do new things, let me sort of go back and remind you of old things which have motivated a lot of developments after that. So this is the Poincaré-Birkhoff theorem. Basically, Poincaré studied this problem, as we all know. He was mostly interested in the planar case, but I mean, he did many things. But amongst those things, he was interested in trying to find periodic orbits, right? Because he considered them to be the skeleton of the dynamics and so on. And sort of he came up with this two-step approach in the planar case, which is the following. So the first step is try to find a global surface of section for the dynamics. So this means, we have the planar case, so we're looking at a three-dimensional level set. And imagine that you're able to find a surface inside that three-dimensional level set with boundary such that the boundary consists of periodic orbits, and it moreover has the property that every other orbit, which are not those, intersect the interior of the surface in finite, in bounded time in the future and in the past. Okay, so that's what's called global surface of section because it allows you to reduce the dynamics, the ambient continuous three-dimensional dynamics to a discrete dynamics on the surface of the so-called return map. So the return map is you take any point in the interior of the surface, you follow the flow until it comes back. That's the first return map. That actually, in this case, preserves area. It's an area-preserving map of a surface, and it encodes all the dynamics of the system because this is a global section. And in particular, it encodes periodic orbits because by construction, the periodic orbits of the original system are in 1-1 correspondence with periodic points of the return map. Okay? So this motivates the second step. So if you are able to find a general fixed point theorem for the return map saying that under some conditions, then there should be infinitely many periodic points, then you found periodic orbits by construction. Okay, so this is exactly the setting of the Poincaré-Birkhoff theorem. So Poincaré conjectured in 1912 or so that, if this return map, which preserves area, moreover satisfies a twist condition, so if it twists one boundary component in one direction and the other boundary component in the opposite direction, then there should be many periodic orbits, so at least two fixed points and infinitely many periodic orbits. So he proved it in some cases, and then Birkhoff, after Poincaré died, proved it in the general case in 1913. Okay, so that's sort of the story. And then many people consider this development to be one of the starting or the cornerstones for the development of modern symplectic geometry because of what happened later, the Arnold conjecture, Floer theory, and so on. So in some sense, we're trying to close the circle in the sense, use the tools that these developments have inspired throughout the years in the original problem. So the goal is to try to generalize this approach to the spatial problem. So what is the global surface of section for the spatial problem, and can we try to get a fixed point theorem for the spatial problem as well, which generalizes the classical Poincaré-Birkhoff theorem. So that's sort of what I want to explain today. So and explain the developments that we got. Okay. Any questions? Okay. So let me sort of delve into step one. So what is the higher dimensional notion of a global surface of section? Is what we call a global hypersurface of section. And for this, I need to introduce also a related notion, which is an open book decomposition. So if you studied contact geometry or contact topology, you probably are familiar with this notion already because of the work of Giroux, who tells you that basically studying contact manifolds or contact structures is the same thing as studying open books up to some operations. So the idea is the following. So the definition is an open book decomposition on a manifold M is a fibration defined on the complement of some codimension 2 submanifold B, and take the values in the circle. And I want that this fibration is standard on some color neighborhood of B. I want B that to have a trivial normal bundle, so I can trivialize, take a color neighborhood of it. And I want to be able to take polar coordinates on the D2 factor normal to this manifold, and the theta coordinate is exactly what this angular coordinate. I want that to be the fibration coordinate near the binding. So B is called the binding of the open book. So what this tells you is that, modulo some codimension 2 submanifold, the manifold fibers over the circle. The notation that I normally use is say that M is the open book with page P and monodromy phi. So here, the page is just the closure of a fiber. So and B is the boundary of all pages, which is called the binding of the open book. And phi is a monodromy, which is a diffeomorphism of the page, which is like a gluing map. So the idea is you take a book, right? You open it up, you see all these pages of the open book having boundary on the binding of the open book, and then you do something which you should never do to a book. You glue the front cover to the back cover with some map, okay? And then you see this picture that I'm drawing here. So you see the binding sitting in the middle, and then sort of the pages all radially coming together on the binding again, and then away from the binding, away from this sort of neighborhood, then you get some sort of vibration over the circle. Okay, so this is a very sort of general notion in the sense that every odd dimensional manifold which is closed can be presented in this way. So you can present any manifold, for example, any 3 manifold can be presented in this way. So it's actually very general. So you can vary the page, you can vary the monodromy in the map and class group of the page. Okay, and then so far it's only a notion in a smooth topological notion, but it also relates a lot to dynamical systems because of the following definition. So you assume that now you have a flow on your manifold, and then you have an open book, and then you want to say that the open book is adapted to the dynamics of the flow if the binding of the open book is invariant, and moreover, orbits are transfers to the interior of all pages with bounded return time to any of those pages. Okay. So you should imagine that the dynamics of my flow is sort of wrapping around the binding, sort of crosses every page, and in bounded time. So if you look at it from above, project down to the circle, orbits sort of rotate around the circle in a positive direction. They never come back. Okay? So you get some sort of like global sense of rotation of the dynamics around the binding. If you have this, then each page becomes what we call a global hypersurface of section. So it's a codimension 1 submanifold whose boundary is invariant, and then the orbits away from the binding or away from the boundary meet interior of all pages transversely in bounded future and past time. Okay, so this is the same thing as a global surface of section, but in higher dimensions. So in this situation, we also have a Poincaré return map F, which is defined a priori on the interior of the hypersurface of section. It's a very subtle problem to understand whether the map extends to the boundary or not. I will say a bit more about that later. But a priori, it's only defined on the interior. Okay. All right, so then with this preliminaries, let me state the first term that I want to state. This is a result that we obtained with Otto already in 2020, so 5 years ago. So you take a bounded regularized NHC surface in the spatial CR3BP, so near the Earth or near the Moon again. So remember topologically, this is S3 times S2. But now it has an invariant subset, which is a spatial, the planar problem, which is an RP3 inside S3 times S2. And the theorem says you take any parameters for the system, so any mu and subcritical C, which is the lower, we're still working in the low energy range. Then the theorem says, okay, the regularized energy level set can be presented as an open book, sort of abstractly. So where we understand what the page and the monodromy is. So the page is a four-dimensional manifold. It's a disk cotangent bundle of S2, diffeomorphic to the disk cotangent bundle of S2. This is what generalizes the annulus to the spatial case. And then the monodromy is a squared of a map which was well studied by Arnold and Seidel. It's called now the Den-Seidel twist. So it's a symplectomorphism of these stars too. And we're looking at the square of that map. And the content of the theorem is that this open book, which we understand absolutely, is also concretely adapted to the dynamics. Okay, so I can find my vibration and I can adapt it to the given flow without touching the flow in order for it to be adapted and in order for us to have a return map. Okay. The binding of the open book is the planar problem itself. Okay, so we knew from before that it's an invariant subset. Now what I'm saying is that I can realize the planar problem as the binding of an open book decomposition for the spatial problem. And the topology of the open book as well as the monodromy and the page are all completely understood. So again, as in the general case, it reduces the dynamics to that of the return map. The return map now is a map from a four-dimensional manifold to itself, and it's actually Hamiltonian. So this page of the open book, as I will explain later, is actually a symplectic manifold with boundary. The boundary is the planar problem because it's the binding of the open book. And this map actually preserves that symplectic structure. And the important thing here to note is that this section, I mean, this open book is non-perturbative, so it's there for any value of mu. I'm not starting with, say, the integrable case and then perturbing and finding my open book. I'm starting with arbitrary values of the parameters. And moreover, it's explicit. I can actually write down the open book for this spatial problem. Of course, I cannot write down the return map because that would imply integrating the equations in some sense. But I can write down the vibration and then work in local coordinates. So this is, of course, good for numerics. So if you're trying to visualize the map, for example, that you get, you can use sort of the fact that you have coordinates and try to sort of understand what the map is doing. Of course, this is complicated because this is a four-dimensional map, but there are ways to study high-dimensional maps and visualization for those. Okay, and then another remark is that we can actually push the open book. We know that there's an open book all the way up to L2. Okay, so there's also a return map, but we don't know whether it preserves a symplectic structure as soon as you go above L1 and a bit, because we don't really know whether the contact structure extends all the way up to L2. Okay.
So you can say nothing about the higher energy levels?
Not really, because now once you go higher up, then the levels has become non-compact for not for collision reasons, but because you have unbounded hill regions, and then all this ideas of, I mean, okay, that's not entirely true. So a piece, let me try to be vague a bit. So a piece of this open book So everything that's away from collision still extends to all values of the energy. That's a very simple computation that you can do. Um, so, I mean, basically, the Hamiltonian, you can write down some sort of vibration such that the Hamiltonian vector field is transverse to the fibers of that. But then, if you're in a non-compact setting, your satellite or your small mass can go to infinity, and then you don't know whether it comes back. So you don't know whether it rotates because it could go to infinity. I
Okay,
don't know.
okay.
I mean, the topology of the levels has changed so drastically that you need different tools, basically. Yeah. Any other?
One more question. You also mentioned numerics. I mean, and my question is, does this approach uh, work better than those like from the analytic perspective?
I mean, you don't have any analytic results
Yeah, I
yet. I
mean,
mean,
not analytic results, but I mean this three-body problem and looking for closed orbits is a very old problem, and there were many approaches from the um, not from the geometric point of view. So my question is whether the geometry here helps somehow.
I think so. Yeah. I mean, I'll maybe ask me this question when I finish the talk because then
Yeah,
I'll
it's
explain
sorry.
how
Yeah,
I
yeah, yeah.
how I want to find periodic orbits. Um, as you say, there are many different ways of try to approach the problem. But as soon as you're away from a perturbative scenario, then most of the tools that we know break down. I mean, of course, numerical tools are still there, so you can still use many of those. Um, but yeah. Anyways, yeah. Let's discuss this after. I think
Yeah, yeah, sorry.
better. Okay, so this is the first set of theorem. So as far as I can see, it completely kills step one of this program. We've done all we could. I don't think you can really improve it as much as I can, as far as I can see. Um, and maybe a comment like we don't know an analogous theorem like this for the planar problem, uh, in the sense that it holds for any values of the parameters. We know that there's an open book that exists for some values of the parameters with so-called convexity range. You need some sort of convexity to get those open books for the planar problem. But after that, you don't know whether that extends. So that's called a Birkhoff conjecture, or some people call it the Birkhoff conjecture. So the spatial problem is different. So this theorem tells you that the open book is always there. So from the perspective of finding the open book, it turns out that the planar problem is harder than the spatial problem, which is heuristically is a bit surprising, or it was surprising to me at first. Okay. Anyway, so that's step one. What about step two? Okay, can we try to get a fixed point theorem? And this is where some of the tools from modern symplectic geometry will come in. So in a nutshell, we will use Floer theory to try to address this. Let me sort of first say a few words about the setup. If you take a page of the open book, let's call it a W. Um, as I said before, there's a contact form alpha for the spatial problem, whose wave field gives us the dynamics for the spatial problem. And the derivative of alpha restricted to the interior of a page is actually a symplectic form, basically because the wave field is transverse to the page, because it's adapted. Um, and the return map actually is a symplectomorphism, so it preserves the symplectic form in the interior of the page. So this is a map that we want to study that reduces the dynamics of the original continuous flow to now the discrete dynamics of this map, right? But there's a technicality at the boundary which is not minor. It's actually it's a feature of the setup that we ignored for a long time, but now we actually address, which is the following. So there's a trade-off here. So either you can choose that the map extends smoothly to the boundary because me and Otto proved that it does. I mean, it's not for free. So you can choose that it extends smoothly to the boundary, but the symplectic form actually degenerates at the boundary. And the problem of the symplectic form degenerating at the boundary is because the wave vector field becomes tangent to the boundary. And remember, the wave vector field is the kernel of the alpha. So the symplectic form has to degenerate at the boundary, but then you can actually fix that degeneration. You can sort of change coordinates, and now you can turn omega into an actual non-degenerate two form along the boundary. But the price that you pay is that the map no longer extends continuously to the boundary. Okay, so either you choose your geometry to be nice at the boundary, or your dynamics to be nice at the boundary, but you cannot choose both. Okay, so and that's a feature of the setup that you cannot bypass. And it's interesting to realize that it also holds for billiards. When you study billiard maps, you have the same type of trade-off. The
Sorry,
study, yeah.
Agustin, just a question. Which one of these two options is easier to deal with in general, in particular cases, non-continuously or degeneracy?
Well, okay, good question. I mean, first of all, this is what I was going to say now. So first of all, they're equivalent to each other. Okay, you go from one to the other. Okay, you can conjugate. There's a map that takes one from the other, which I call a square root map, because you should really think it's a square root. It's sort of continuous at the origin, but not smooth at the origin. But now what was easier for me was to choose B. So in what follows, I will choose B because now I don't have to I have to worry about the geometry of the problem. It's standard at the boundary, but I will have to deal with the dynamics. So I will have to now have a map which is only continuous at the boundary, and I have to do something about it. I knew how to deal with that, but not with the other case. I don't know, but maybe
Thank
somebody
you.
else.
It seems interesting. I think that it's worth it. Thank you.
Yeah. So
just a quick question. It looks very familiar to B symplectic geometry. Does it, I mean, is it related?
So the B symplectic.
Yeah,
No,
B
really.
symplectic.
So the B symplectic is a singularity thing. So you have a pole at the boundary. This is more like a zero. It's not. It's you don't have the local models for singularities like you do in a
Okay.
case. Yeah, it's not the same thing. There's also another confusion. I don't know if some people have worked with ideal Liouville domains. This is also not that. Okay? This is a different thing. This is what I would
Thank you.
call a degenerate Liouville domain. But if I choose B, the symplectic form extends as a symplectic form to the boundary, and then we have what's called a Liouville domain. So it's an honest Liouville, like an honest symplectic manifold, which is exact, whose boundary is contact type. So the boundary is the planar problem. So this is why I choose my geometry to be nice, because I know how to work with Liouville domains. Okay. So now basically we have a map which is C0 at the boundary, but it's defined on some Liouville domain. So that's what we have now. So let then F be a map in a Liouville domain, and I look at the contact form at the boundary. The contact form, remember in the previous setup, at the boundary is a contact form for the planar problem, okay? Not for the spatial one, but for the planar problem. Maybe I should have called it a different letter. Anyways. So I will define a notion of a twist map in this setup, and I will define it as follows. So my map, I will say it's a Z0 Hamiltonian twist map if the first condition is that it's Hamiltonian in the interior, so it's generated by a C1 Hamiltonian, which might in general depend on time. Remember, a common confusion is that this Hamiltonian is defined on the page of the open book, so it has no relationship whatsoever a priori with the Hamiltonian, give you the original Hamiltonian for the CR3BP, okay, which is autonomous. Well, it's defined on a different manifold. Okay, so this Hamiltonian might depend on time. It's defined on the page and it generates the return map, and it's at least C1. And then there's the extension problem. So both F and the Hamiltonian admit continuous extensions to the boundary, but not necessarily C1 extensions to the boundary. So this is the big pain that I will have to deal with. Okay, and then the third condition, which is a crucial condition, is what we call the weakened twist condition, because before we had a stronger version of the condition. So what I want is that near the boundary, the generating Hamiltonian vector field satisfies that. If I look at the Hamiltonian vector field of that Hamiltonian, and if I plug it into the contact form at the boundary, so this measures the transversality with respect to the contact structure, I want that function, which might depend on time in general, to be strictly positive. So this is positively transfers to the contact structure at the boundary, and I want that function as I approach to the boundary to explode to infinity. Okay? So the intuition is something like being positively transversed to the contact structure is my sort of positivity condition at the boundary, or my twist condition. And as you approach the boundary, I want that twist condition to be sort of more extreme in the sense that it explodes to infinity. So basically have an infinite twist map. So a map that's infinitely wrapping at the boundary. And in some sense, that's sort of what remains from the degeneracy problem that we observed before. You have some explosion behavior at the boundary. Okay, so this is the definition of that I want to work with, Hamiltonian twist map. And the theorem, so this is a result that I obtained with my student Arthur that we based on a previous result of mine with Otto. So the main proof is the same basically, but the difference is now when we actually deal with this degeneracy problems. So the theorem is you take a C0 Hamiltonian twist map on a level domain and you assume three things. So, and I want to stress that these three conditions are not very strong, so they're quite mild. So first, this is not really a condition. I want to assume that all fixed points of the map are isolated, which means by compactness that there's finitely many of them. This is not a problem because if it's not satisfied, then I already found infinitely many fixed points. Okay. I already won. So this is not a problem. The second condition, I want to assume that the first term class is 0 if the dimension of the manifold is at least 4. So this has to do with grading in symplectic homologies and the Floer homology of the manifold. It's also a mild condition. Most Liouville domains satisfy that. And then the third condition has to do with now really the Floer theory of the manifold. So, I don't want to say too much about Floer theory, but a Liouville domain has an associated symplectic homology, which we denote SHW. It's some vector space, which is usually infinitely generated, and this is what I want to assume. So the condition is, I want to assume that this vector space is non-zero in infinitely many degrees. So there's a degree because of the second assumption, that's 1 equals 0. So it's an integer valued degree, and I want to assume that on infinitely many of those, this vector space is non-zero. And the conclusion is the same as the Poincaré-Birkhoff theorem. So there's simple interior periodic orbits of arbitrary large minimal period. Okay? So here minimal and simple are redundant. So what I'm saying is that I'm not finding periodic orbits which are sort of iterates of the same point of the same orbit. Right? I'm finding geometrically different generators, geometrically different periodic orbits. Okay? All right, so one comment, sort of, we also have a version for Hamiltonian chords. So this is for periodic orbits, but we also have a version for Hamiltonian trajectories, which are not periodic. So they start in a Lagrangian and they finish in another Lagrangian. And we need to sort of replace symplectic homology by the corresponding Floer homology, which is called Rapp-Floer cohomology. Okay. Anyways, and then another thing that I want to say is that this condition, the third condition of symplectic homology, as I said, conjecturally symplectic homology is either 0 or infinite dimensional. Basically this would correspond to the infinite dimensional case. So we expect that condition to actually we should be able to relax it to just having non-vanishing symplectic homology. And this would follow from applying Ginzburg's approach to the Conley conjecture using symplectically degenerate maxima. Anyway, so this is just a tangential comment. Okay, so that's the theorem that I want to present. For cotangent bundles, the theorem simplifies quite a bit, and I'll state that in a bit. But let me just first compare it to my previous result with Otto. So the point now is that this twist condition that we're using is an open condition. So it just has to do with the vector field being positively transverse to the contact structure. That's C1 open condition. Before with Otto, we were using a twist condition which wasn't open because we asked that the vector field should be parallel to the ray vector field at the boundary. That's not an open condition. So this is an improvement on that. The boundary degeneracy is actually addressed, whereas before we assumed that everything was nice, the Liouville domain and the map extended smoothly and so on. Now we actually address this feature of the setup. And then the third condition was a bit more technical, which just goes into how we prove it. But we replace what we used before using action, the Hamiltonian action in Floer homology. We replace it, before we used index growth, so the index in homology, but now we're using action. So there's the two things that you could do with this Floer theories. You have a action filtration, or you have a grading. So we're basically replacing one for the other. But one thing that I want to emphasize is that in both results, there's no assumption on the non-degeneracy of orbits. So orbits could be degenerate because in real life, if you have an actual system like the three-body problem, the Hamiltonian will have all sorts of degeneracies. But luckily for us, there are ways to deal with that. I mean, I learned how to deal with degenerate problems from the work of Ginsburg, and there's also work of Hingston and finding geodesics and things like this. They all use some sort of local version of Floer homology or local homology in general. Okay, maybe that's sort of a bit of a technical point, but this is a comparison. And this is a special case that I mentioned already for cotangent bundles. So the first remark is that if you have an orientable manifold, then the C1 of the cotangent bundle is automatically 0. So the second condition is not really a condition. And the symplectic cohomology of a cotangent bundle is well known to be isomorphic to the cohomology of the loop space on the base. So this is huge dimensional for most manifolds, in particular for spheres. And here in a fiber-wise star-shaped domain is, if you're not familiar with that, it's just a domain in a cotangent bundle whose boundaries transfers to the fiber-wise radial direction. So it's basically the Liouville domains that you find in cotangent bundles. So the special case of the general theorem is you take an orientable enclosed manifold, you take a C0 Hamiltonian twist map as we defined it on a fiber-wise star-shaped domain, then the conclusion is the same as before. It has periodic orbits of arbitrarily large minimal period. So this because the symplectic cohomology condition is satisfied, and the C1 condition is also satisfied. Okay, and the case for S2 is the one that's relevant for the CF3BP. So in that case, the page of the open book, you can actually view it as a fiber-wise star-shaped domain in T star S2. Okay, so that's sort of the theorem that I wanted to present. I mean, now how much time do I have? Maybe 5 minutes, something like this.
10 minutes, I would
you-
say.
Yeah, but I think that you can even stay a little bit longer. Don't
Okay.
worry much about that.
No, okay, thanks. I probably won't take all that much. All right, so basically the situation right now is we have the hypersurface of section, we have the open book. We managed to reduce the problem to studying these maps on a 4 manifold. We have a general theorem, which is this one. But now the problem is the twist condition. Okay, the only obstruction to applying this theorem is basically checking the twist condition, which implies finding a Hamiltonian that generates your map satisfying the condition that I explained. And that's actually much harder to do than we thought. Okay, even in the integrable case. So in the integrable limit case, in the rotating Kepler problem, we can write down an open book. We can write down the return map explicitly. It's basically a rotation with some pseudo angles. We can even write down generating Hamiltonians for that map on the page of the open book, but those Hamiltonians do not satisfy this condition as I defined it. It doesn't mean that there's not another Hamiltonian that satisfies that, because the Hamiltonian is not fixed, right? The only thing that's fixed is the time 1 map, the map F. This the Hamiltonian generating it is auxiliary. But in general, if you give me a map and then ask me find the generating Hamiltonian for that map, that's not an easy question to address. I mean, as far as I know, if you guys know how to do that, then that would be great. But anyway, so that's the situation where we stand right now. Okay, so and then having said that, maybe I'll say a few words about how you prove this theorem. I mean, at least what the main ingredients that go into the proof, and then I'll call it a day, and then just open the floor for questions. So the proof of this theorem requires 3 steps actually. So the first step is the step addressing the problem at the boundary. So the C0 condition. I want to basically express my map F, which is generated by some Hamiltonian H, as a limit of maps F, which depend on some parameter epsilon, which I will call the smoothing parameter. It's a limit as epsilon goes to 0 of a bunch of maps. And those maps are actually C1 Hamiltonian twist maps in the sense that they extend to the boundary. as a C1 map. And those maps should be generated by Hamiltonians H, which depend on epsilon, which are also some sort of smoothing of the original Hamiltonian H, with the property that when you plug in the Hamiltonian vector field of those maps to alpha, so you get this function, I want that to be positive also. And I want it to diverge as epsilon goes to 0, because I get then the infinite twist map for the original map, while the other derivatives of epsilon stay bounded. So in other words, if I fix my epsilon, this function is actually finite. So it's like would be like a twist map which twists a lot, but a finite amount of time. And as epsilon goes to 0, this a lot grows, like 1 over epsilon, say. So you express an infinite twist map as a limit of finite twist maps, which twist more and more. So that's sort of the intuition. So once you've done that, you can do the following. So now we know that this map, this Hamiltonian H epsilon extends to the boundary. Therefore, I can extend it to the completion. The completion of W, which is W hat, it's just you have your manifold with boundary, then attach a cylindrical end to the boundary. So something of the form boundary of W times R. It's like a cylinder, like an infinite cylinder. And now, because my Hamiltonian extends to the boundary, I want to extend my Hamiltonian to a Hamiltonian H epsilon hat, with the property that it's actually linear at infinity. So it's a linear Hamiltonian. It depends on it's of the form slope times r plus b, where r is a radial direction, as a radial coordinate. And the reason I do that is because those Hamiltonians are the ones that are used in the definition of symplectic cohomology. So the way that this works is symplectic cohomology is actually a limit as epsilon goes to 0 of this the Floer homologies of this extensions. The point here is that the slope of this Hamiltonians grows to infinity as epsilon goes to 0. And these Floer groups are generated first by periodic orbits of this H epsilon Hamiltonians. And because as the slope grows larger and larger, I'm observing longer and longer periodic orbits at the boundary. So that's basically in a nutshell the definition of symplectic homology. You define a Floer homology for an admissible Hamiltonian, so something that's linear at infinity, and then you take a limit where the slope goes to infinity. That's how you connect sort of the dynamics that we care about, so the right-hand side, with the symplectic geometry of the manifold, which is the left-hand side. Okay, and then the third point, and this is the last one. So I want, in this setup, remember that periodic orbits of the return map, which are not in the planar problem, are those which are spatial orbits, which are interior periodic points of the map. Okay, because remember that the boundary of the manifold is the planar problem. So the interior periodic orbits are the ones which I'm interested in. So whatever fixed point theorem that I prove should give me the existence of interior periodic points as opposed to boundary periodic points. But in order to separate boundary from interior, I need some mechanism. And the mechanism that I will use is exactly this action growth condition. So the point is that under some condition, which is here, which I'll explain in a bit, under this condition, the Hamiltonian action of orbits which are at the boundary grows to infinity. Okay, so they escape any finite action window. Therefore, they do not contribute to the limit. They do not contribute to symplectic homology in the limit as epsilon goes to 0. I mean, that's sort of the idea. So the quantitative twist condition which I'm using is some sort of quantitative version of the twist condition that I just defined. It's the following two conditions. So the first one is I want that the Hamiltonian is positive at the boundary, which is not much of a condition on its own because I can always shift my Hamiltonian without changing the dynamics. But the second condition is what plays against the first condition. I want that the max at the boundary of the Hamiltonian is strictly less than the min of the derivative in the radial direction of the Hamiltonian at the boundary. Okay, so it's some sort of C1 quantity being larger than a C0 quantity. So I can sort of shift in order to make A hold, but I can't. But in order to have the second condition hold, I cannot really shift all that much. Okay, and under this, observed because of the Hamiltonian being positive, this the second condition B implies that this derivative is positive, which is a weak twist condition as I defined it before. So this condition here. So the quantitative twist condition implies the twist condition. Okay, and under this quantitative disk condition, one can prove, and this is fairly straightforward, that the Hamiltonian action with respect to the extension of a periodic orbit at the boundary satisfies an inequality of this form. So it grows to minus infinity with the period. So the larger the period, the smaller the action, and this is sort of it grows to minus infinity in a linear in a what is it in a at least linearly. Okay. All right, so these are the three steps, and then basically the first observation that we need to make is that first we are assuming that this derivative is exploding to infinity as epsilon goes to 0. Therefore, this condition will be true for epsilon sufficiently small. Okay, so this is not really a condition because of the first step. So this is the first observation. So by step 1, the quantitative twist condition is for free under the weakened twist condition. Okay? Because the smoothing parameter makes everything explode to infinity without sort of, the left-hand side explodes, whereas the right-hand side stays bounded. Okay, so therefore, there are no contributions from boundary orbits of the extension of the smoothened Hamiltonian to the symplectic homology. Therefore, the generators of symplectic homology correspond to interior periodic orbits. So that's sort of the key point, how we deal sort of with boundary versus interior points. And then the theorem, assuming step 1, step 2, step 3, finishes by the following argument, which is, I think this is like the core of the proof. And it's actually a rather clean way to approach it, I think. So the statement is, well, the way you prove it is, assume by contradiction that you have finitely many periodic orbits, x1 up to xn, and assume they have some periods m1 up to mn, which are greater than 1. So these are the periodic orbits with period greater than 1. And then gamma 1 up to gamma k are the fixed points, so the periodic orbits of period 1. Okay, so I will try to get a contradiction. So I will say the following: take a sequence of primes going to infinity. So basically here I'm using the existence of infinitely many primes. So Peter Sarnak actually told me that when I gave this talk at the IIS, and I hadn't realized that I was actually using that. So he was happy, and I guess so was I. Anyway, so using the existence of infinitely many primes, take a sequence of them that goes to infinity, and then look at the inverse of that. So I call that epsilon I, that goes to 0 as I is large. Therefore, my smoothing parameter sort of recovers sort of in the limit the original system. And I assume that these primes are larger than the max of this periods, MJs. So the point now is now symplectic homology, I can realize it as the limit of Floer homologies, where I'm taking the Hamiltonian, which is the pith iterate of the smoothing of the original one. So the pith iterate just means that the one periodic orbits of this Hamiltonian is just pi periodic orbits of the original Hamiltonian. So the period is growing to infinity as with I, and the parameter is also the smoothing parameter is going to 0. So therefore, in the limit, I recover dynamics for the original Hamiltonian. So now the arguments as the following. I will choose some, I mean, by assumption, I'm assuming that symplectic homology is supported in infinitely many degrees. So let me take n such degrees, and I take n to be larger than the dimension of the manifold times k. K is a number of fixed points. And I take n degrees, I1 up to In, such that the corresponding homology in those degrees is non-zero. Therefore, because of this limit, the corresponding Floer groups in those same degrees are not 0 for I sufficiently large. And now all I do is try to understand what are the possible periodic orbits that can contribute to this Floer group. So remember that all you need to know for that is that the orbits that can contribute to this Floer group are pi periodic orbits of h hat epsilon I. Okay, so, or in other words, because everything is interior, you can drop the hat and you can drop the smoothing. So it's just pi periodic orbits of the original Hamiltonian. Okay, so now since pi is prime, if I take a periodic orbit xj of period mj, it cannot contribute to this Floer group, because the only way that it could contribute to this Floer group is if I iterated that orbit. But now the period of that orbit is the prime pi times something else, but that would divide the corresponding prime here. So because I'm taking primes, they're non-divisible by powers of the X-rays. So the X-rays cannot contribute to this Floer group. So the only generators that could possibly contribute are those which are just iterates of the one periodic orbits, because one divides the prime. Let's assume for simplicity that these are non-degenerate, therefore they have well-defined degrees. Here I'm using the fact that we have a well-defined degree in symplectic homology, which is the Conley-Zander index. But now, there's k of these orbits, so they can cover at most k degrees, and this is a contradiction because n is greater than k. You need to be able to cover at least n degrees, and that's basically, in a nutshell, the contradiction. So you have more homology to generate than generators, if you assume finitely many periodic orbits. The degenerate case is a bit more technical. I mean, you cannot really assume that these orbits are non-degenerate, but it turns out that when you perturb those orbits, there's a finite number of non-degenerate orbits which appear, and the degrees of those non-degenerate orbits are bounded by a bound which is just the dimension of the manifold. So this explains the appearance of this dimension of W here. So each of those orbits can correspond to at most k times dimension of W degrees, but I take n to be greater than that, and the contradiction is the same. And there's a formal way to package this in a spectral sequence, but I won't get into those details. So that, in a nutshell, is the proof. So maybe just to summarize and to conclude, we've been looking at the three-body problem. We are trying to find periodic orbits. We're following the same ideas of Poincaré and the spatial problem from the planar one, so namely trying to find a section, which we already did, and then trying to find a fixed point theorem that applies for the return map. We have those theorems. The problem, they say under a twist condition, then you have periodic orbits. The problem is now checking the twist condition in practice, at least for, say, the integrable case, which we even then are not able to do, but hopefully try to do that for the integrable case, and then using the fact that it's an open condition and perturb and get some perturbative result for existence of periodic orbits in the spatial problem, which are spatial periodic orbits as opposed to planar orbits. Anyway, so I think that's all I wanted to say. So thank you.
Thank you very much. So are there any questions, remarks? Okay, if not, I have one. I mean, going back to the question about going beyond low energy range. Okay, in general, I agree that you get not compact Hill regions, but what if you go like slightly beyond low energy range? Then you still have a compact Hill region.
That's a good question. Actually, I didn't state that, but we proved that. So what's true is that if you go slightly above L1, you still have a contact manifold because it's an open condition. And we actually found an open book for that one. The topology of the open book is like a connected sum. There's a simple formula for that. And all the results hold. So, all that I said holds for slightly above L1.
Okay.
And the open book, as I said, also extends all the way up to L2, but we need more work to try to understand, because there's a result of Robert Nichols that shows that the contact condition is lost at some point. But I think that only holds for near the rotating Kepler problem. So it doesn't really say that you lose the contact condition for all the other parameters. So that might be the case that you still have it. And then you will fall into this scenario again.
Okay.
I mean, the problem being that you don't know whether, that there's a return map, but you don't know whether it's a symplectomorphism a priori.
Okay, thank you. Any more questions? Well, I would like to go back to the question about numerics and the role of the geometry there. Could you comment on that more?
So Right. So the role of geometry is basically perspective. Like it gives you a section, so it's a four-dimensional section for the spatial problem, and it's a simple game. So for example, you would take a point in the plane, okay, and then shoot orbits upwards. Assume that the energy is fixed and below L1, so that you come back. Therefore, you'll go up, reach a maximum, go down, puncture the plane, reach a minima, and then come back up. And then you would record where you came back. So that's a Poincaré map, basically. It's a very simple thing. So the geometry sort of helps you basically connect that picture to the topology of the open book. But now, once you're there, you would just integrate a lot of orbits and try to see if you can find some structure in the return map by visualizing it. So you see now you're beyond the geometry. Now you're just basically doing numerics, but visualization. I mean, you're not doing hard analysis or anything like that. You're just trying to understand, what this map looks like in some sense. And hopefully, I mean, we're doing that with some engineers, and hopefully that will guide us and try to prove theorems, or at least what to expect.
Okay, but does it simplify things in the numerics? In some
Well,
sense?
I'm not the person to answer that question. I'm not doing the numerics, but I don't think it's
No, I mean, me neither. I'm just asking out of curiosity.
I think it's just guides the numerics. Like
Okay.
simplifies them.
Just one question, Agustin, because I hope you hear me well, because I have a little some problems with the microphone and everything. But
It's fine.
okay, listen, we have your theoretical results are very nice, are very interesting, and it could be nice to know which parts of your research you think if they could be further generalized, in which direction. This is one question. The other question,
I missed the question because your mic is playing games.
once again.
I didn't hear your question. Sorry.
Yeah. My question is, I have two questions. The first question is, which parts of your research you think you could generalize or make more general to deal with more cases? This is the first one. And the second one is, we have people here in this seminar sometimes applying things, studying the free body problems from the dynamical point of view, dynamical systems. Which parts of your research you think could be more useful to apply to practical problems, not numerical? I mean, for example, you talked at the beginning about the Hill radius and things like that. Which all the topics you think you could apply it to? Okay,
let me try to answer the second question first. So, I mean, this is my theoretical approach to the three-body problem. I also have more applied approach that I've been following with engineers, but like directed to trying to organize families of periodic orbits for the systems. The orbits come in families because you can vary the energy. You fix mu, you vary c, you get a family of orbits, but then you get bifurcations and all things like this. And we've done quite a bit of work and try to come up with tools that are directed to organizing all of these families, coming from symplectic geometry.
That's cool, indeed.
That's sort of the more applied stuff. I'll be happy to. I mean, I didn't discuss that today because I thought maybe people found this more interesting, but I'm also happy to discuss that at some point.
Well, yes,
yeah.
we find interesting everything you said, but as I said, we have two things in this seminar. Things that we like, things about symplectic and contact geometry, because some of us we have even works in the topic, and on the other hand, it was applied it then to practical problems. So this is the mix. Maybe numerical is too much for us. Even when I have tried once in my life twice. But from time to time, we have engineers trying to work with us. So this is very cool to know about periodic orbits and all this typification and things of the sort. So it's interesting.
Yeah. Well, thanks. But yeah, as I said, I mean, this is my attempt to try to find periodic orbits. And then what I saw that could come out from the open book picture is that one that I just mentioned. It would be some sort of like, I don't know how much you can extract from it, but it would be some sort of game that you can play and try to visualize things. Because I mean, and I've also seen plenty of engineers doing visualizations for four-dimensional Poincaré maps. So it's not, yeah, it's not like an unreasonable thing to try to do. But that's sort of the one thing that I can think of coming out of this picture of the open book for a more applied direction. But all the other applied things that I've done are different from this, are not exactly sort of connected to this. Yeah, I mean, if you guys have more ideas of where these things could be used, I mean, I'm all ears and happy to discuss.
For sure, in the future, I hope we will have, because with Xavi, for example, we were collaborating with someone from the University of Barcelona, and we were
Yeah.
trying to do this stuff with dynamical systems. So let's see what happens. Well, for sure, it would be nice if you can send us what your results, some work or archive preprint about these families of solutions.
Sure, for sure. Yeah, I can do that. No problem.
Are there any questions? Any more remark? Okay. If not, thank you, Agustin, for very interesting and clear talk.
My pleasure.
Thank you all for attending, and let me announce the next speaker.
Bartosz, one thing, Agustin, maybe we can upload your talk to our YouTube, because
Yes.
we called it for the students, for our students. Take a look. Thank
Sure,
you.
no problem.
So the next speaker is Manuel de Leon, who will talk about new geometric structures in thermodynamics. So once again, thank you for your talk, and see you next week.
Thank you, Agustin.
Oh, okay, take care. Bye-bye.
Pleasure. Bye. Thank you.